What is this? What happened to my costume? This isn't where my eyes go! And what do you call this? What happened to my nose? I can't work like this. Where's my agent?
Hey, Holly baby, it's no big deal. Marketing called. Kids don't want talking Komodo dragons anymore. They want Picasso. So we pulled some strings and look, you still have all your old parts, and you're gonna be the hottest thing since that cartoon dog detective.
With my eyes like that, I can't see. I'm a monster! Ah! What were we talking about?
Chemical reactions.
Chemical reactions are all over the place, from the center of the sun to your own cells. So what is a chemical reaction?
Chemical reactions are just ways of rearranging the same old atoms to make something different.
You already know that all the matter in the universe already exists. You can't make more atoms and you can't destroy any atoms. But you can move atoms around. That's where chemical reactions come in. The constant rearranging of atoms is what makes the world go round.
The written version of a chemical reaction is a chemical equation. It's kind of like a basic addition problem. You add up the reactants over here and put the product over here. In the middle, we use an arrow instead of an equal sign.
When you read a chemical equation out loud, you can say yields when you get to the arrow. Yields is just another word for makes. Now, before you get really into chemical reactions and equations, there are a few things you should know.
First of all, the atoms in the reactants over here also have to be in the products over here. You can't just go around adding atoms and throwing them away whenever you want to. I mean, what do you think you are? Mick Jagger?
Since we're trying not to lose any atoms, it's important to know how many we started with. So the first step in working with chemical equations is to count the atoms on the reactant side.
How do we count atoms, you ask? Well, sometimes there are little numbers sort of below the chemical symbols. Those are called subscripts, and they tell you how many of each kind of atom is in each molecule. If there's no subscript, it means there's only one atom of that type.
You might also see a bigger number in front of each molecule. That's a coefficient. It tells you how many molecules you're working with. If there's no coefficient, you know you have one molecule.
Got that? Subscripts count atoms. Coefficients count molecules. To count the total number of atoms, multiply the subscript on an atom by the coefficient on its molecule.
Let's see how this works. Here we have 3 molecules of NH4. We know because of the 3 here in front. We also know there's 1 nitrogen atom in each molecule because there's no subscript after the N. You can even write in the 1 if you want to. We multiply that by 3 molecules to get 3 nitrogen atoms total. When we move on to the hydrogen, we see that there are 4 of them in each molecule. We multiply 4 hydrogen atoms from the superscript by 3 from the coefficient. That's 12 hydrogen atoms.
Oh, and one more thing. Sometimes you'll see a little S, L, or G in parentheses after each molecule. Those tell us which phase of matter each molecule is in, solid, liquid, or gas. Sometimes scientists also use the letters AQ, which stands for aqueous. Aqueous means dissolved in a solution. Make sure to pay attention to those little letters because sometimes they change during the reaction.
Let's put this all together and check out a real reaction. Over here we have CH4 or methane gas. That's 1 carbon atom and 4 hydrogen atoms. Then we have O2 or oxygen gas, which is a molecule made of 2 oxygen atoms stuck together. But wait, the coefficient of 2 tells us there are 2 of them. Since 2 times 2 oxygen atoms equals 4, we actually have 4 oxygen on this side of the equation.
Now, when we add the reactants up, everything moves around, but the number of atoms doesn't change. Let's check out the products.
CO2 has 1 carbon and 2 oxygens. And over here we have 2 water molecules. That's 2 hydrogens and 1 oxygen multiplied by 2 to give us 4 hydrogens and 2 oxygens. When we add it all up, it looks like every atom of reactant is also on the product side. We're good to go.
Hey, you said all atoms have to be on both sides of the equation. But what if they don't match up?
That's a great question, but hold your horses. That's stoichiometry, and we'll tackle it another day. For now, don't worry about it. What you really need to know is that the atoms on both sides of a reaction should match up.
Precipitation reactions.
Hey, what do you have when you mix two liquids and get a solid?
Magic!
The actual answer is a precipitation reaction.
I'll show you a great precipitation reaction. I'll show you the precipitation reaction of your dreams and your nightmares. Abra Cadabra!
That's a great precipitation reaction.
Is what I meant to do.
A precipitation reaction is a special kind of chemical reaction where two liquids combine to make a solid. The solid is called a precipitate, hence precipitation reaction.
The magic happens when two ionic compounds are dissolved in water. Both compounds fall apart, so the water is swimming with positive and negative ions. The negative ions from the reactants switch places to bond with positive ions and form new ionic compounds.
Scientists write the form for a precipitation reaction as AB plus CD yields AD plus CB. See how the ions switch dance, partners?
This kind of reaction is called a double displacement reaction. Displace means take the place of. So double displacement occurs when both ion pairs split up and rearrange. Makes sense, right?
I get it, but why do I need it? Well, it's not always obvious how your reactants will recombine. If you want to predict the products of a reaction, you'll need to know which ions are likely to match up.
There are a few different rules you can follow when you're trying to figure it out. We'll use this example to keep track of our options.
First, remember that ionic compounds have to be neutral in charge. That means the two bonding ions can't have the same charge. So you know all the pairs will include a positive ion and a negative ion. We can break the equation down and match up pairs of positive and negative ions.
You can also cross off a couple options by looking at the reactants. The products on the right won't be the same as the reactants on the left. So you know anything that just makes the same thing won't work.
That only leaves one more option. The new compounds must be BaCrO4 and 2KNO3.
There are actually two ways to spot a precipitation reaction. First, look for the double displacement format. If two ionic compounds rearrange themselves, you're on your way. Otherwise, check the phases of matter. If two liquids react to make a liquid and a solid.
Houston, we have a precipitate.
Great! Consider yourself a pro at this stuff.
Good. It's very good.
Come on, dude.
Oxidation reduction reactions.
It may seem like all this chemical reaction stuff is just one big molecular square dance, but sometimes it's more like a rave in the dark with electricity. Ooh.
Some reactions are about electrons more than whole atoms. In fact, anytime an atom or ion gains electrons, it's called reduction.
That's dumb. Why do they call it reduction when electrons are being gained?
It's actually called reduction because its original meaning had to do with getting pure metals out of rocks, which still doesn't really sound like reduction. Just go with it.
Anyway, the opposite of reduction is oxidation. That means to lose electrons. And get this, oxidation doesn't always involve oxygen. It's all about electrons.
Oh, the folly of our industrial chemists' forebears. If it were up to them, we'd call dogs cats and sushi a T-bone steak. Pish!
Actually a handy way for you to remember all of this, though. Just think oil rig. If you spell it out, that's oxidation is loss, reduction is gain.
Now, an atom won't give away electrons unless they have a place to go, right? And it can't pick up electrons unless they come from another atom or ion. That means oxidation and reduction always go hand in hand, like peanut butter and chocolate, or pizza and ranch dressing, or hedgehogs and capybaras. Okay, since they're always together, scientists call reactions that include them redox reactions.
Redox reactions are different from precipitation reactions because they're all about transferring electrons during bonding. It's the change in charge that makes the atoms rearrange.
Redox reactions are usually single displacement reactions, which means there's only one atom switch going on. Scientists write this kind of reaction as AB plus C yields AC plus B.
With all this electron swapping going on, scientists need tools to track the motion of electrons. That's why they write down oxidation numbers as they go and keep things simple with equations called half equations.
An oxidation number tells us the number of electrons that have been taken from an atom or ion.
For ionic compounds, oxidation number is the same as electrical charge. Ionic bonds happen when atoms exchange electrons, so it makes sense that gaining and losing electrons changes the charge of the ions. But things get a little more complicated when atoms share electrons, like in covalent bonds. In fact, the oxidation number shows what would happen if all covalent bonds were ionic instead.
So what you're saying is they're pretending the bonds are ionic.
No! Chemists never pretend! Chemists are not children!
Okay, yeah, they're pretending, but it's useful pretending. It helps them keep track of lots of electrons when the chemistry gets complicated later on.
See, the more electronegative an element is, the more negative its oxidation number gets. It just can't stop stealing electrons from other atoms. You could also say it's reducing because it's gaining electrons. Reduction is gain, remember? Less electronegative elements have a harder time hanging on to their electrons, so their oxidation numbers tend to be higher. Every electron they lose means they oxidize more. Let's look at an example.
Since carbon has 4 valence electrons and spaces for 4 more of them, it can have a charge of either positive 4 or negative 4. When it bonds with 2 oxygens to make carbon dioxide, the oxygens hog the 2 bonding electrons because they're more electronegative. That means carbon has a charge of 4, but its oxidation number went from 0 to 2 because it lost 2 electrons, or it would if those bonds were ionic.
On the other hand, when carbon bonds with 4 hydrogens to make CH4, it's the one with an iron grip. Carbon is more electronegative than hydrogen, so the electrons are drawn to it. In fact, if they bonded ionically, hydrogen would have to say bye-bye to its electrons. In this case, carbon has a charge of -4, and its oxidation number is also -4. It stole an electron from each hydrogen atom. The hydrogens each have an oxidation number of 1.
The bottom line is charge and oxidation numbers sometimes go together, but sometimes they go their separate ways, so watch out!
You could figure out oxidation numbers by counting every electron that's been removed from every ion, but that would take forever. Instead, here are a few tips to help you keep track of what's where.
First of all, the oxidation number of a plain element is always 0. If it hasn't reacted with anything, it hasn't lost any electrons.
If a molecule is made up of one kind of atom, then its oxidation number is the same as its charge.
If a molecule has more than one kind of atom in it, the oxidation number is the same as the sum of the oxidation numbers of all its atoms.
And here are a few handy rules for specific elements. Fluorine always has an oxidation number of -1. Oxygen usually has an oxidation number of -2, except when there's an oxygen-oxygen single bond, in which case its oxidation number is -1. Hydrogen has an oxidation number of +1 in covalent bonds.
That's one tool scientists use to track electrons. The other is half equations.
A half equation is, wait for it, an equation split in half.
Wow, thank heavens.
Let's try that again. Half equations split an equation into 2 simpler ones that show exactly which electrons go where. To see how they work, let's jump in and try one.
The first step to using half equations is to separate all the ions in the full equation. When we separate this equation into ions, we have 1 magnesium, 2 hydrogens, and 2 chlorines turning into 1 magnesium, 2 chlorines, and 2 hydrogens. Good. Now it's all out there.
See the little plus and minus signs after each ion? Those are oxidation numbers. That's what we're here to keep an eye on.
Get it? Eye on.
You might notice that almost all the ions changed oxidation numbers during the reaction. That's good. A change in oxidation number means they're exchanging electrons, which means they're a working part of the reaction.
The only ion that stayed the same was the 2Cl. It appears on both sides of the equation, but its oxidation number stayed the same. That means it didn't react with anything. In fact, it's called a spectator ion because it just standing around watching the reaction. Get it out of there.
That's better. Now we have Mg plus 2H plus yields Mg2 plus H2, which we can split into two half equations. The first half reaction is all about hydrogen. If we just look at what happens to hydrogen, we see two hydrogen ions with oxidation numbers of +1 on the reactant side and two neutral hydrogen atoms on the product side. Somewhere, those positive ions picked up a couple of electrons. We add a little 2e minus to the reactant side to show exactly what happened during the reaction. The other half reaction shows us what happened to the magnesium. We have neutral magnesium on the reactant side, but on the product side, magnesium has an oxidation number of +2. The magnesium ion lost 2 electrons. Since we know that hydrogen gained 2 electrons, we can be pretty sure where they went.
Half reactions help us see exactly what's happening on the electron level of a chemical reaction by focusing on one element at a time. Cool, huh?
So what do we do with all this? Well, the answer is all kinds of stuff. Redox reactions are the beginning of what we call electrochemistry. Electrochemistry is what happens when a chemical reaction produces electricity. And hey, if you have a phone or a computer or even a toy dog that does backflips, you can thank electrochemistry. It's what powers every battery on Earth and beyond.
Electrochemistry also includes electrolysis. That's using an electrical current to create chemical change.
So how do we get electricity out of a redox reaction? Well, there's a transfer of energy when the electrons move from one atom to another. But it's not really doing any work yet. It's just energy.
So how do we put those electrons to work? The key is to force them to move. If we separate the electron donor from the electron acceptor, we can make the electrons take a trip between them, put them through a wire, and we call it an electrical current. Zzz.
Ah, yes, the electrical current. I remember swimming as a boy in the river of Edison's most stunning creation. I reached out to the source of power and was transported to a land of fire and then blackness. And when I returned, I had the most glorious abilities, such as... Oh, now it's dark. Mommy!
Kinetics.
Can't sit still. Too much energy. Too much to do. Stay in motion. Everybody's talking about motion. Motion makes chemistry happen. Motion is key. Motion, motion, motion.
Chemistry is all about motion, or kinetics, as those fancy science types like to say.
Not all reactions happen at the same speed, not even close. Some reactions happen in the blink of an eye, and some take hundreds of years. Scientists use a model called the collision model to explain why some reactions are faster than others. The collision model says that chemical reactions happen when molecules crash into each other, and those crashes don't really happen unless the molecules are in motion.
To be specific, chemical reactions happen when molecules crash hard enough for their chemical bonds to break and they split apart. The amount of energy needed to break those bonds is called activation energy. Scientists write it as EA.
The collision model might sound familiar. Remember the gas laws? Molecules zipping around, crashing into each other? Well, a lot of the same rules apply to all chemical reactions. The more molecules collide, the faster the reaction goes.
There are a couple of different ways to speed up a reaction. Speed up the molecules involved, or force them closer together.
So we can speed up a reaction by making the molecules go faster. One really great way to do that is by adding heat to the equation. Higher temperatures make the molecules move faster, and that makes them more likely to collide.
We can also force more collisions by putting lots of molecules into a small space. There are a couple of ways to do this: increase the concentration or increase the pressure.
Concentration matters because molecules are more likely to collide if they're crowded. You can increase concentration by adding more molecules.
If you can't add more molecules, you can always raise the pressure, which does almost the same thing. Increasing pressure forces all the molecules closer together. Either way, the reaction speeds up.
Reactions also depend on how reactive your reactants are. Some elements, like the noble gases, pretty much keep to themselves and don't really react. And some, like the halogen group, can't wait to mix it up. This goes all the way back to the periodic table, but really, reactive elements react faster than more stable ones.
The last thing that affects the speed of a reaction is the surface area of the reactants. If you think about it, reactants won't react if they don't have anything to react with. The more parts of a reactant are exposed for the world to see, the more likely it is to react.
Think of it this way. A big chunk of a reactant might have lots of molecules in it, but they won't react if they're on the inside. A reaction would have to start on the outside and work its way in. If we take the same amount of a reactant and make it into a powder, the reaction will go faster because more of the reactant is accessible.
And one more thing. Sometimes a reaction needs some help getting started. So, chemists use a chemical called a catalyst to get the party going. A catalyst is a substance that jumpstarts a chemical reaction without getting involved in the reaction itself.
Catalysts are super important. In fact, your body is full of catalysts called enzymes. They make sure your body takes care of all kinds of processes that wouldn't happen fast enough without them. If you can sit there and watch this video, think an enzyme.
So we know reactions happen at different speeds. But how can we tell how fast a reaction is moving?
Well, little buddy, the speed of reaction is called its rate of reaction. You can't find the rate of reaction just by watching it, because the rate might change over the course of the reaction. Instead, scientists measure rate of reaction by keeping track of how fast one of the reactants is used up.
There are a couple of ways to keep track of the reactants. First of all, scientists can try to measure the concentrations of the reactants as the reaction goes. If the reaction doesn't happen too fast, they can take samples every once in a while and see how much reactant there is left.
If the reaction causes an explosion or is just too quick to measure, they can also use the products to figure out how much of the reactants were used. Both of these strategies work best for reactions that involve liquids or gases, since they're easier to test for concentration than solids are.
The written version of all this is called a rate equation. It tells you how quickly or slowly your reactants are being used up. The rate equation takes the form rate equals k times a to the x times b to the x.
First, let's look at how the equation is put together. Rate is the measurement of how quickly the reactants turn into products. So it's measured in moles per unit of time. That's usually seconds, but it could be minutes or something else.
And what's with the funny lines around A and B?
Those are brackets. Anytime chemists use brackets in an equation, it means concentration of. So this equation uses the concentration of reactant A and the concentration of reactant B.
Okay, so what about those little tiny things? What are those? X's?
Those represent the order of reaction. See, once they know how fast their reactants are being used, scientists use a number called the order of reaction to express how important each reactant is to the rate of reaction. After the experiment, the X's are replaced with numbers. Which numbers, you ask?
If the order of reaction is 0, it means that reactant has nothing to do with how fast the reaction goes. On the other hand, an exponent of 1 means the relationship is directly proportional. That's called a first-order reaction.
Wait. What's directly proportional?
Directly proportional means that the reactant makes the reaction go forward. And if a little makes it go forward a little, a lot makes it go forward a lot. So, a first-order reaction is one that moves faster when the reactant is added.
An exponent of 2 is called a second-order reaction, and it means the rate of reaction is proportional to the square of how quickly the reactant is being used.
That means the reactant is even more important to the rate of reaction. Say you double the amount of reactant. The reaction would move 4 times as fast. Add 4 times as much reactant, the reaction would move 16 times as fast. When it comes to second-order reactions, a little more goes a long way.
Each reactant in a chemical equation has its own order of reaction, but scientists add them together to make one number for the whole equation.
Now, how do scientists figure out reaction orders? The old-fashioned way. Every reaction has a different order of reaction. There's no way to determine orders of reaction except to do the experiment.
When you write rate equations, you can use this little symbol, which means is proportional to. Or you can use an equals sign and add a little rate constant we call K.
Constant? More like an anti-constant. In fact, it changes all the time. It only stays the same if you're just changing the concentrations of the reactants. If you change the temperature or the activation energy, or if you add or take away a catalyst, the constant changes.
The rate constant K rolls a bunch of different numbers into one big number. Some of them are big and complicated, so we won't talk about them here. But they include temperature and activation energy. If either of those changes, so does the rate constant.
To see how this works in the lab, let's check out a quick problem. Now, usually you'd have to set up an actual experiment to test for order of reaction and rate law. Lucky for you, our top secret scientists have already run the reaction and made a handy data table. Somebody send those guys some chocolate.
So the actual identity of the reactants doesn't really matter here. Let's say we're dealing with reactant A, reactant B, and some products. The table tells us that our team ran the reaction 3 times, switching up the concentrations of the reactants each time. Since these concentrations are for the beginning of the reactions, we call them initial concentrations.
The key here is to compare the reaction runs and see what changed. We can start with the first 2 runs. When we compare run 1 with run 2, we see that reactant A stayed the same, but reactant B doubled. And so did the rate of reaction.
Since the concentration of reactant B and the rate of reaction increased by the same amount, we know they're directly proportional. That means the order of reaction for reactant B is 1. We can go ahead and write in an exponent 1 after the B.
Now let's look at run 2 and run 3. Here, the concentration of reactant A doubled and reactant B stayed the same. And the rate of reaction also stayed the same.
Since the rate of reaction didn't change when reactant A changed, we know that reactant A has no effect on the product. That means the order of reaction for reactant A is 0. Write that thing in.
Now that we know all the orders of reaction for this experiment, finding the rate law for the whole reaction is a snap. Add up the exponents and you have the rate law for the whole thing. In this case, the order of reaction for reactant A is 0. So the rate law is the constant K times the concentration of reactant B.
Hey, awesome! But there's one more thing. With all this information, we have everything we need to find the rate constant K. All we need to do is plug in the numbers our scientists came up with when they ran the reaction.
Remember, K is different every time scientists run the reaction. Why don't we find K for experimental run number 3?
We know the rate law for our reaction is rate equals K times B. Using our table, we know the rate of reaction is 2.5 times 10 to the negative 2 meters per second.
We also know the concentration of reactant B in run 3. It's 2 molar. We can solve for K by dividing both sides of the equation by 2.0 molar. In this case, the constant K is 1.25 times 10 to the negative 2. And hey, you win! Now you know the rate law and the rate constant for this particular reaction.
Equilibrium.
Equilibrium is another word for balance. Dynamic is a fancy word for moving. Dynamic equilibrium happens when 2 opposite reactions happen at the same rate, at the same time. They cancel each other out, so they just keep happening.
Think of it this way. Joe rides his bike over to his friend Kara's house to drop off her pet snake, Cartwright. What he doesn't know is that Kara is riding a different route on her own bike to bring Joe some crickets for Cartwright's dinner. If each route takes the exact same amount of time, they'll get to each other's houses and turn around. And they're back where they started. That's dynamic equilibrium.
Chemically, the equation for a reaction at dynamic equilibrium has arrows going both ways. The reaction is moving in both directions at once. It's super important to realize that a reaction at equilibrium might look like it stopped happening at all. But don't worry, it's chugging away behind the scenes. In fact, that's how you know the forward and backward reactions are happening at the same rate. If they didn't line up exactly, you would see a change.
Warning! Be careful. Equilibrium doesn't mean the amounts of reactant and product are the same. It's just the rate of each reaction that's the same.
Equilibrium can be physical or chemical. A closed jar of lemonade never seems to evaporate, right? That's because the number of molecules evaporating and the number of molecules condensing back onto the surface of the lemonade is the same. Since it's losing and gaining molecules at the same rate, it looks like nothing's happening. Oh yeah, dynamic equilibrium.
The same thing happens chemically. Say some molecules of reactant collide and react to form a product. Then say the molecules of the product collide hard enough for their bonds to be broken. They turn back into reactants and the whole thing starts over again. If those two chemical processes happen at the same rate, boom, dynamic equilibrium.
What happens if something in a system at equilibrium changes?
Well, a guy named Le Chatelier decided to find out. We call his findings Le Chatelier's principle.
Le Chatelier's principle says that a system at equilibrium will try to stay at equilibrium. That means it deals with any changes in a way that brings the whole system back to equilibrium.
Let's check in with Joe and Kara. Say Kara's dad sees what's going on and offers to drive her over to Joe's. They're no longer moving at the same speed, so the whole system's out of whack. According to Le Chatelier, the system would try to slow Kara down again, tax in the road, or a construction detour. Ah, that's better.
Now let's look at this in more chemical terms. Say we start with this equation, but then we dump in a bunch of extra reactant A. That messes up the equilibrium of the reaction. But according to Le Chatelier, the system will correct itself.
In this case, reactant B will go into overdrive to use up reactant A and make it into C plus D. We say this shifts the equilibrium towards the products because the reactants are definitely not in equilibrium. Eventually, the whole system settles into a new routine.
Ah, equilibrium.
Nuclear reactions.
There's one more type of chemical reaction you should know about, and it's a big one. We've been over precipitation reactions and redox reactions, but what about nuclear reactions?
Most atoms have nuclei that stick together because of the strong force, but certain isotopes of certain elements aren't so stable. To become more stable, they get rid of energy by kicking out bits of the nucleus. Isotopes that lose parts of the nucleus are called radioactive isotopes. The process of losing those parts is called a nuclear reaction.
Nuclear reactions don't involve any bonding or switching of atoms. They happen in the nucleus, hence the name.
Stable atoms strike a balance between protons and neutrons. Trouble happens when they have too many of either one. If things get out of balance, the nucleus falls apart.
The process of losing parts of the nucleus is called radioactive decay. And there are a few different ways this can happen.
Sometimes, a nucleus loses a piece of 2 protons and 2 neutrons. That little piece is called an alpha particle, and this kind of decay is called alpha decay.
Alpha particles are like helium nuclei under cover. They have 2 protons and 2 neutrons.
Losing a couple of protons is more than enough to turn one element into another. For example, uranium is an element with 92 protons, but when it goes through alpha decay, it becomes thorium, which only has 90 protons.
Alpha particles are pretty heavy for their size, so they don't travel very far once the nucleus spits them out, only about an inch. This kind of radiation won't hurt you as long as it's coming from outside your body. It's not even strong enough to break through your skin.
Beta decay is another kind of radiation. It's what happens when an electron shoots out of the nucleus. Now,
Hey, you don't fool me. There aren't any electrons in the nucleus.
Okay, you're right. There aren't any electrons in the nucleus. But I'm not lying to you. During beta decay, one of the neutrons splits into a proton and an electron. The nucleus spits the electron out and keeps the proton. We call the electron a beta particle. That means the atom loses one neutron and gains a proton, so it turns into a different element.
For example, cobalt-60 is an isotope of cobalt that's involved in the fallout from lots of nuclear weapons. It starts out with 27 protons and 60 neutrons, but when it begins beta decay, each atom turns into nickel. Now it has 28 protons and only 59 neutrons.
Beta radiation is a little more dangerous than alpha radiation. Since electrons are small and fast, they aren't as easy to protect against. But a sheet of aluminum foil will still keep you out of harm's way.
The third kind of radioactive decay is called gamma decay. No particles fly off of the nucleus this time. Instead, gamma decay happens when the nucleus gives off a little burst of energy called a gamma ray. The ray is made of photons, which are the little packages of energy that make up light. Gamma decay sometimes happens after beta decay, but it doesn't change the number of protons and neutrons in the nucleus.
Gamma radiation is much stronger than alpha or beta radiation. It can only be stopped by something really strong and thick, like lead or a really thick layer of concrete. That's why the dentist makes you wear a lead apron when you get x-rays.
We humans try to avoid radiation, but sometimes it can be pretty useful. One way scientists use radiation is in carbon dating. That's a way of figuring out how old things are by measuring the radioactive isotopes in them. In fact, all living things absorb some radioactivity through an isotope called carbon-14.
Ah, I'm radioactive! Get it off, it's all over!
Whoa, calm down. You do have a little radiation in your body, but it's all because you eat plenty of vegetables. See, we get carbon-14 when particles from outer space enter Earth's atmosphere and collide with nitrogen to make new carbon atoms. Plants absorb them as carbon dioxide, and people and animals absorb them when we eat the plants. So I think you're going to be okay.
Oh, okay.
Anyway, scientists figure out the ages of old things by using half-life. That's how long it takes half a chunk of an element to break down into something else.
We know that it takes about 5,730 years for half of a chunk of carbon-14 to decay into nitrogen. It takes 5,730 more years for half of that chunk to decay, and another 5,730 years for half of that chunk to decay. Get it? Half-lives are different for each isotope, but they're pretty predictable. That makes them super helpful to scientists.
By measuring the amount of carbon-14 left and comparing it to the half-life of 5,730 years, scientists can figure out an object's age pretty accurately. They've used carbon dating to find the age of all kinds of things.